Hello, my dear students. Welcome to everybody to my channel, STEM Educator and Innovator Suresh. I think all of you are well and fine by this pandemic period of time. And today, I want to discuss with you about chemistry. So, don't be late. Let's start now. Hurry up. Hello, everyone. Welcome again. We entered into the channel and we want to be introduced with the channel. Enter here to acquire knowledge and be out for the welfare of mankind. That's the theme of this channel. And what is STEM? I think you know. S stands for science, T for technology, E for engineering, and M for mathematics. We are well known about STEM. Okay. Now we want to be introduced about the topic. S level means advanced subsidiary level. There exist 3 papers: paper 1, paper 2, paper 3. And in paper 1 there exist 40 marks. For paper 2 there exist 60 marks, and duration it is 1 hour and 15 minutes. So book references, name of the book is Cambridge International S and L level chemistry course book. Author is Laurie Ryan and Roger Norris, and obviously the publisher it's Cambridge University Press, 2nd edition, ISBN 9781107638457. Today we will discuss about chapter 1, and the name of the chapter is moles and equations. Well, masses of atoms and molecules. First of all, we have to define a relative atomic mass, AR. The relative atomic mass is the weighted average mass of naturally occurring atoms of an element on a scale where an atom of carbon-12 has a mass of exactly 12 units. In equation, mathematically we can present this relative atomic mass AR of an element Y. Suppose it is equals to average mass of one atom of element Y multiplied by 12 divided by the mass of one atom of carbon-12 isotope. And then we have to define a relative isotopic mass. So, in order to find out a relative isotopic mass, first of all we have to know what is called isotope. Isotopes are atoms that have the same number of protons but different numbers of neutrons. Always they are the atoms of same element. Okay. The term relative isotopic mass for the mass of a particular isotope of an element on a scale where an atom of carbon-12 has a mass of exactly 12 units. For example, the relative isotopic mass of carbon-13 is 13.00. Relative molecular mass, MR, we have to define it. The relative molecular mass of a compound, which is symbolized as MR, is the relative mass of one molecule of a compound on a scale where the carbon-12 isotope has a mass of exactly 12 units. Relative formula mass. What is relative formula mass? For compounds containing ions, we use the term relative formula mass. So, sometimes we be confused which one relative molecular mass and which one is relative formula mass. I think it will be clear from the definition of each of them from here. This is calculated in the same way as for relative molecular mass. Ways are presenting in the same way, but it is specially stand for ionic compounds. Now, accurate relative atomic masses, it is usually found out by using mass spectrometer, and the process is called mass spectrometry. A mass spectrometer can be used to measure the mass of each isotope present in an element. Okay, how the mass spectrometer work out? It is shown by this schematic diagram. Beginning part, heated filament produces high energy electron here, like a coil here. It is nothing but heated filament. And then we want to see here the downward arrow indicates the vaporized sample through which it is being entered, and both high energy electrons and here the vaporized sample, when mixed with each other, they become ionized. That's why this is called the ionization chamber. Then this ionized one is passed through positively charged electrode. After that, we'll see there is a flight tube through which the ions are moving, below that there exists a magnetic field, okay, and after that it will enter to the ion detector, okay. Ion detector detecting result will be recorded to a recorder, and finally it will send to the computer, okay, and computer will show graphical presentation, okay. We want to see the mass spectrum produced shows the relative abundance, isotopic abundance, which is also called, on the vertical axis, and the mass ion ratio m by e on the horizontal axis. So we are getting from here the information which is being recorded by the computer we observed by the previous mass spectrometer. Determination of relative atomic mass from mass spectra. To calculate the relative atomic mass, we follow this method. First one, multiply each isotopic mass by its percentage abundance. Add the figures together, second one, and then divide by 100. Okay, so the mass spectrum of neon has 3 peaks like this. 20 neon 90.9%, 21 neon it's 0.3%, and 22 neons it is 8.8%. Okay, so if we want to find out the relative atomic mass or isotopic mass of this, air of neon equals to 20 multiplied 90.9 plus 21.0 multiplied 0.3 plus 22 multiplied 8.8 divided by 1000. After calculating using calculator, we'll get 20.2. Okay. Next, we want to see amount of substance, the mole and the Avogadro constant. First of all, we want to define mole. 1 mole of a substance is the amount of that substance that has the same number of specific particles. Means, what is particle indicating? It means atoms, molecules or ions, as there are atoms in exactly 12 gram of the carbon 12 isotopes. Okay, the number of atoms in a mole of atom is very large, you know, and it is in 1 mole the number of particle, look at this, how big the number is. It's very large, 6.02 into 10 to the power 23 atoms. If it be atom, then if it be molecule, there will be 6.02 into 10 to the power 23 molecules. If it be ion, it will be 6.02 into 10 to the power 23 ions. Even if it be number of human beings, oh amazing, so then it will be 6.02 into 10 to the power 23 human beings. But it's totally impossible, because in our planet near about 800 crores of people are present, so it will not be possible to present 6.02 into 10 to the power 23 human beings. This number is called the Avogadro number. Don't forget it. 6.02 into 10 to the power 23 is called the Avogadro constant or Avogadro number. The symbol for Avogadro constant is L. The symbol Na may also be used in different time. You will see in upper class. Moles and mass, we want to see number of moles equals to, in short, moles is written as mole equals to mass of substance in grams divided by molar mass in gram per mole. Next, another expression for number of moles is equals to number of particles divided by Avogadro number. Another expression stands for this given volume by molar volume, and another expression for calculating number of mole is mass of substance in grams, molar mass in gram per mole. Another one, concentration in mole per dm cube multiplied by volume in cubic centimeter divided by 1000. Most of you like this one. Number of moles equals to concentration into volume divided by 1000. It's familiar with all of you, but don't forget it. You have to use the conversion factor 1000. If the volume is given in dm cube, need not to divide by 1000. Bear in mind. But if the volume is given in cubic centimeter, then you have to use the conversion factor 1000. You have to convert cubic centimeter into dm cube by using 1000 as division. Mole calculations, reacting masses. We want to see how can we calculate stoichiometry. At the time of solving mole and the reacting masses, we should know what is stoichiometry. the ratio of moles of the reactants and product is the stoichiometry of the equation. Okay, so look at this. In order to find the mass of products formed in a chemical reaction, we use the mass of the reactants, the molar mass of the reactants, and the balanced equation. Don't forget it. These three things are very important to find out the mass of products formed in a chemical reaction. We want to solve a problem based on the discussion we already done, and it is problem solving 1. Iron 3 oxide reacts with carbon monoxide to form iron and carbon dioxide as the reaction given here. So already it's a balanced equation. Iron 3 oxide reacting with 3 moles of carbon monoxide to form 2 moles of iron and 3 moles of carbon dioxide. Now the question is asking to you, calculate the maximum mass of iron produced when 798 gram of iron 3 oxide is reduced by excess carbon monoxide, where relative atomic mass values for iron is 55.8, for oxygen that is 16.0, it's given. Now we have to see how the solution will be done. Step 1. First of all, we have to rewrite the equation. Iron 3 oxide reacting with 3 carbon monoxide to form 2 moles of iron and 3 moles of carbon dioxide. Step 2. 1 mole iron 3 oxide equivalent to 2 moles of iron. If we search the equation, look at the reaction, we are getting 1 mole of iron 3 oxide is equivalent to 2 moles of iron. Now, if we convert them in masses, we will see total mass for iron 3 oxide is this, and it's equivalent to, for right side or the product, 2 into 55.8. So in left side, iron 3 oxide formula is Ap2O3, means 2 atoms of iron, 2 multiplied by 55.5 plus 3 atoms of oxygen, 3 multiplied by 16.0, and in right side only 2 atoms of iron, so 2 multiplied by 55.8. Now summing up or calculating it by your calculator, you will see 159.6 gram of iron 3 oxide is forming 111.6 gram of iron. Step 3. Unitary method. Since the question is asking you to find out the maximum mass of iron produced, given amount of iron 3 oxide is 798 gram. Look at this. So by using the unitary method, 159.6 gram is producing 111.6 gram iron. 1 gram will be divided by in right side by this one, and 798 gram it's forming. We have to multiply this value by 798 and it is forming 558 gram iron. Problem solving 2. Tin 4 oxide is reduced to tin by carbon. Carbon monoxide is formed here, and in symbolically, if we want to see tin 4 oxide reacting with carbon 2 moles to form 1 mole tin plus 2 moles of carbon monoxide. Calculate the mass of carbon that exactly reacts with 14 gram of tin 4 oxide. You have to give the answer in 3 significant figures. It's important. You have learned a lot from mathematics about the significant figures. If the question asked that you have to present the answer in a particular significant figure, whether it will be 2, 3 or 4, you have to maintain that, otherwise you will be penalized by mark reduction. Okay, and also extra information given here. Relative atomic mass for carbon is 12.0, oxygen is 16.0, whereas tin is 118.7. Now we have to solve it. Step 1, we have to write the equation given, and it's already balanced. Tin 4 oxide, 1 mole react with 2 moles carbon, 1 mole tin and 2 moles of carbon monoxide is forming. Now step 2, we are observing from the reaction 1 mole tin 4 oxide equivalent to 2 moles of carbon. Okay, so we have to convert it in mass. 118.7 gram is the relative atomic mass of 1 atom of tin, and then 2 atoms of oxygen, 2 into 16, it's forming 2 moles carbon, is 2 into 12.0, we have to write the calculation 150.7 gram of tin 4 oxide equivalent to 24.0 gram of carbon. By calculation using calculator. Step 3, by unitary method, we can say 1 gram of tin 4 oxide equivalent to 24 by 150.7 gram of carbon, and the amount of tin 4 oxide given here, look at this, it's 14.0 gram. So it's equal to multiplied by 14 the previous value, and by calculator it will give you 2.23 gram carbon nearest 3 significant figure. Now we want to learn more about the stoichiometry of a reaction. Stoichiometry is the field of chemistry that is concerned with the relative quantities of reactants and products in chemical reactions. For any balanced chemical equation, whole numbers, that is the coefficients, are used to show the quantities generally in moles of both the reactants and products. For example, when oxygen and hydrogen react to produce water, 1 mole oxygen reacts with 2 moles of hydrogen to produce 2 moles of water. All of them are in whole number. Now we want to see coefficients are presenting here by writing number as a prefix of its element or its compound. Okay, look at 2 stands for 2 moles hydrogen reacting with, there is nothing written. So some of you be confused like that, what will happen here? Nothing. There exists 1 mole oxygen, and after the reaction it is forming 2 moles of water. Now, well, significant figures, we want to learn more about it. Significant figure, it's very important for AS Cambridge syllabus or A2, because sometimes you'll see the questions are asking to give the answer finally in significant figure in a particular number. We want to see an example. When we perform chemical calculation, it is important that we give the answer to the number of significant figure that fits with the data provided. Okay, the examples show the number 5 to 6.84 rounded up to varying numbers of significant figures. We want to see how can we convert it in different indicated significant figures. Round to 4 significant figures will be 5 to 6.8. Okay, number 1, 2, 3, 4 significant figure. It will be eliminated because if it be 4, it's less than 5, so it will be totally eliminated. Rounded to 3 significant figures, it will be like this. Look at this, 0.8 is near 26.8, 526.8 nearest 27. So in 3 significant figure, we have to write 527. But if it is asked to round it to 2 significant figures, then it will be 530. It's important. Percentage composition by mass. Another topic in a compound, percentage composition means percentage of any element present in a given compound is the percentage composition by mass. Okay, its formula to find out is equals to atomic mass of an element multiplied by the number of moles of particular element in a compound divided by the molar mass of that compound multiplied by 100%, since it is converting in percentage. Okay, now problem solving 3, we want to see percentage calculation by mass. Calculate the percentage by mass of iron in iron 3 oxide Fe2O3, where the relative atomic mass values iron is 55.8 whereas oxygen 16.0. Percentage mass of iron equals to 2 into 55.8 divided by the total formula mass is 2 into 55.8 for iron plus 3 atoms of oxygen is 3 into 16.0 multiplied by 100%, and after calculating by using a calculator you will get 69.9%. Next one is important for you, empirical formula. Though you have learned in O levels what is empirical formula. The empirical formula of a compound is the simplest ratio or simplest whole number ratio of the elements present in one molecule or formula unit of the compound. Key points here. The formula of an ionic compound is always its empirical formula. Ionic compound's formula is nothing but its always empirical formula. Okay, don't forget it. The empirical formula and molecular formula for simple inorganic molecules are often the same. Often the same, don't forget it. But sometimes it can be different. Organic molecules often have different empirical and molecular formula. So these are the key points for empirical formula. If you remember these three things, you will be very much clear to find out where empirical formula are differing or not. Okay, like this: compound water, empirical formula H2O, molecular formula is 2O, whereas hydrogen peroxide empirical formula is HO and molecular formula H2O2. Next, problem solving 4. A compound of carbon and hydrogen contains 85.7% carbon and 14.3% hydrogen by mass. Deduce the empirical formula of this hydrocarbon, where relative atomic mass for carbon is 12.0 and for oxygen is 16.0. We have to see the solution. So what we have to do? Step 1, we have to note the percentage by mass. Carbon is 85.7 and hydrogen has the percentage by mass is 14.3%. Now step 2, we have to divide each of the values by using the relative atomic mass of the required atom. So carbon 85.7% by mass and its relative atomic mass is 12.0. Dividing, we are getting 7.142, and for hydrogen we are getting 14.3 divided by 1.0 means 14.3. Now we have to divide each of the values by using the smallest value, which is 7.142. Between these two result means the quotient we are getting here 7.14 is the smallest one. By using this smallest value, each of the result or the quotient will have to be divided, and after doing this we are getting here 1 for carbon and it will be the nearest value 2. Always you have to convert quotient into the nearest whole number. Nearest whole is here 2. Now the formula is becoming empirical formula of this compound is CH2. Molecular formula. The molecular formula shows the actual number of each of the different atoms present in a molecule. So it's important, whereas empirical formula shows the ratio of atoms present in a compound, but molecular formula shows the actual number of each different atom present in a molecule. In order to deduce the molecular formula, we need to know, mandatory, we have to know, number 1, the relative formula mass of the compound, number 2, the empirical formula. These two things mandatory to find out the molecular formula. Problem solving 5. A compound has the empirical formula CH2Br. Its relative molecular mass is 187.8. Deduce the molecular formula of this compound. Given relative atomic mass air for bromine 79.9, carbon 12.0, hydrogen 1.0. Okay, now we have to see the solution. Step 1, find the empirical formula mass. We can find out it: carbon 1 atom, hydrogen 2 atoms, bromine 1 atom. So using the relative atomic mass each of them, we are getting 12.0 plus 2 into hydrogen here 2 atoms, so 2 into 1.0, bromine here 1 atom, 79.9 into 1 is forming 93.9. Step 2, divide the relative molecular mass by the empirical formula mass, and it's becoming 187.8 divided by the empirical formula mass. We already get it 93 and equals to 2. You will see by using your calculator it is not exactly 2, but we have to convert it in nearest whole number. Okay, mind it, you have to remember we have to convert values in nearest whole number. Okay, now step 3, multiply the number of atoms in the empirical formula by the number in step 2. That is, the number we get from step 2 we have to multiply by this 2, this one CH2Br. So look at this 2 into CH2Br. So the molecular formula is now C2H4Br2. Are you getting me? Okay, nice. Chemical formula and chemical equations. How can we deduce the formula? Look at this. The formula of an ionic compound is determined by the charges on each of the ions present, and then ions that contain more than one type of atoms are called compound ions. For example, ammonium is a compound ion. Problem solving 6 will illustrate the process totally. Look at this. Deduce the formula of aluminum oxide. What's the formula of aluminum oxide? So ions present here Al3 plus and oxide 2 minus. For electrical neutrality, we need 3 oxide ions for every 2 aluminum 3 plus ions. And how it is being balanced? Look at this. It's become neutral by 3 into 2 minus charge plus 2 into 3 plus charge. And after adding or simplifying, we are getting is equals to 0. It's now charge neutral. So the formula is Al2O3. The formula of a covalent compound is deduced from the number of electrons needed to achieve the stable electronic configuration of a noble gas. This is another important point for covalent compound. We know the formula of a covalent compound is deduced from the number of electrons needed to achieve the stable electronic configuration of a noble gas. Okay, so all the elements usually want to gain the structure of noble gas. That's why they are reacting. So at the time of finding formula of covalent compound, we have to search the electronic configuration, whether it is becoming the structure of a nearest noble gas or not. The formula of methane is CH4 with each carbon atom bonding with 4 hydrogen atoms. One carbon atom is bonding with 4 hydrogen atoms. Okay, by means of that, carbon is getting 4 electrons from 4 hydrogen atoms by making it octet fill to the nearest noble gas, and hydrogen also making nearest noble gas helium structure by gaining or having 2 electrons. Compounds containing a simple metal ion and non-metal ion are named by changing the end of the name of the non-metal element to "ide." So sometimes we will see compound can be formed by combining metal non-metal or non-metal to non-metal. Sodium reacting with chlorine forming sodium chloride. IDE is the suffix here. Okay, so compound ions containing oxygen are usually called ates, like aluminum carbonate or magnesium carbonate, calcium carbonate, all of them as a suffix last it is added ATES means ates, sulfates, phosphates, like that. Balancing chemical equations. How can we balance an equation? A symbol equation is a shorthand way of describing a chemical reaction. We know a symbolic equation represents the totally chemical change occurred there. So how can we balance an equation? We want to see. First of all, step 1, we write down the formula of all the reactants and products. For example, hydrogen plus oxygen forming water. Step 2, count the number of atoms of each reactant and product. If these are not equal, then we have to use the factor. For example, H2 plus O2 is making H2O as product, and then if we count the number of atoms present here, 2 atoms of hydrogen reacts with 2 atoms of oxygen. After the reaction as a product, we are getting 2 atoms of hydrogen but 1 atom of oxygen. Look at the balancing required here. Oxygen atoms are not equal. There is 2 atom and there is 1 atom. So we have to balance here. Step 3, balance one of the atoms by placing a number in front of one of the reactants or products. In this case, the oxygen atoms on the right hand side need to be balanced. We already get it, so that they are equal in number to those in the left hand side. Remember that the number in front multiplies everything in the formula. So you have to remember, when you use a number in front or here, at the time of placing here any number, that will be multiplied with each of the atom present here as a whole. For example, 2H2O has 4 hydrogen atoms and 2 oxygen atoms. Okay, 2 into 2 means 4 hydrogen atoms, and 2 into 1 means 2 oxygen atoms. So 4 hydrogen plus 2 oxygen forming 4 hydrogen plus 2 oxygen. Now this is a balanced equation. Keep balancing in this way, one type of atom at a time until all the atoms are balanced. So finally we are getting the balanced equation is this. Using a state symbols, this is especially important where chemical equilibrium and rates of reaction are calculated. We use the following state symbol: S for solid, L for liquid, G for gas, AQ for aqueous. What is the meaning of aqueous? It's a solution in water. You know, aqua, Greek aqua means English water. So aqueous coming from Greek, and aqueous means solution in water. State symbols are written after the formula, not before. After the formula of each reactant and product. For example, if we want to see zinc carbonate, look at this, ZnCO3 in bracket. After the formula there is S. It is indicating the state symbol. Sulfuric acid aqueous is forming zinc sulfate aqueous, water as liquid plus carbon dioxide as gas. Balancing ionic equations. An ionic equation is simpler than a full chemical reaction. It shows only the ions or other particles that are reacting. Spectator ions are omitted. So sometimes students become confused ionic equation how they will write. Sometimes they are keeping the spectator ions, though they are writing in ionic form, but they are keeping the spectator ions. You have to remember, finally when you are writing an ionic equation, you have to omit the spectator ions or viewer ions. Okay, like that. The ions that play no part in the reaction are called spectator ions. Another name of this is viewer ions. Okay, so writing an ionic equation, you want to see step 1, write down the full balanced equation first. Okay, like this: magnesium solid plus 2 moles of hydrochloric acid aqueous reacting with each other, forming magnesium chloride aqueous plus hydrogen gas. Okay, step 2, write down all the ions present. Any reactant or product that has a state symbol S, L or gas in C or in molecule in solutions such as chlorine Cl2 aqueous does not split into ions. You have to remember this. You never split into ions like this, state symbol having SLZ, or chlorine water or bromine water in aqueous solution. You need not to split in ion. Magnesium solid reacting with hydrochloric acid, we already get it. We know aqueous hydrochloric acid remains as ion, hydrogen ion and chloride ion. So 2 moles of hydrochloric acid, it will form 2H plus aqueous 2Cl minus aqueous. Finally, it is forming magnesium 2 plus equals 2Cl minus plus H2 in gaseous state. So according to the previous step, we can say this will not be ionized. And common ions are here, this one and this one, which are called spectator ions or viewer ions. Those are eliminated from here. Now step 3, cancel the ions that appear on both sides of the equation, which are spectator ions. We are repeating the equation again, and now we are cancelling by red mark. It's totally cancelled out. And now step 4, write down the equation omitting the spectator ions. Final equation is like this: magnesium solid reacting with 2 moles of hydrogen ions aqueous to form 1 mole of magnesium 2 plus ions aqueous and 1 mole of hydrogen gas. Solutions and concentration. Calculating the concentration of a solution is important. That is, now we'll get, that is, the concentration of a compound is given in a reaction or volume is given. Then we have to calculate the number of moles from here. We often need to calculate the mass of a substance present in a solution of known concentration and volume. Usually it can be paper 1, paper 2 or paper 3, anywhere. So to do this, we have to rearrange the concentration equation to this, like moles equals to concentration in mole per dm cube multiplied by the volume in dm cube. Next step, we have to multiply the moles of solute by its molar mass. Another one is mass of solute in gram equals to number of moles, mole in short, multiplied by the molar mass in gram per mole. Okay, so these are 3 equations required to solve this type of problem. Problem solving 7. Look at this. What's the problem here? Calculate the mass of anhydrous copper to sulfate in 55 cubic centimeter of 0.20 mole per dm cube solution of copper to sulfate. Relative atomic mass values here: copper 63.5, oxygen 16.0 and sulfur 32.1. Step 1, 55 cubic centimeter will have to change to dm cube. Okay, change cm cube to dm cube. So equals to volume of copper to sulfate solution 55 divided by 1000, 0.055 dm cube. And step 2, number of moles equals to concentration in mole per dm cube multiplied volume of solution in dm cube, and concentration is given already 0.20 mole per dm cube multiplied by 0.055 dm cube. We already converted previously in step 1. 0.011 mole is the result. Step 3, how can you get the mass? Because you are asked to calculate the mass of anhydrous copper to sulfate. We have just calculated the number of moles, but we know mass equals to moles multiplied by relative molecular mass. So we are getting here previous step 2 0.011 multiplied by the relative molecular mass 63.5 32.1 plus 4 atoms of oxygen present here, copper 2 sulfate. Time of writing the formula, you know, copper 2 sulfate formula is CuSO4, copper atom 1, sulfur atom 1, but oxygen here 4 atoms, so 4 into 16.0. After doing it, we are getting 1.8 gram after 2 significant figures. Calculating solution concentration by titration. Okay, we have to know first the definition of titration. What is titration? I think all of you have learned about it in O levels, but again we want to remember the process of finding the unknown concentration or volume of a solution by using a standard solution is called the titration. Okay, and based on this we want to now do something calculation. Problem solving 9. 25.0 cubic centimeter of solution of sodium hydroxide is exactly neutralized by 15.10 cubic centimeter of sulfuric acid of concentration 0.200 mole per dm cube. Equation is given here. 2 moles of sodium hydroxide reacting with 1 mole of sulfuric acid to form 1 mole of sodium sulfate plus 2 moles of water. Okay, calculate concentration in mole per dm cube of the sodium hydroxide solution. That is the question finally. So look at this, a balanced equation is given, but you are asked to find out the concentration of sodium hydroxide solution. Step 1, calculate the moles of acid. Moles equals to concentration in mole per dm cube multiplied by the volume of solution in dm cube. So look at this, we are telling here dm cube, since the volume is given in cm cube, so concentration 0.200 multiplied by the cm cube volume by 1000. It's finding after doing calculation 0.00302 moles of sulfuric acid. Step 2, use the stoichiometry of the balanced equation to calculate the moles of sodium hydroxide. Okay, so number of moles of sodium hydroxide equals to moles of acid from step 1, okay, multiplied by 2, because stoichiometry from the equation, or it is also called mole ratio. So mole ratio we are getting here 1:2. So number of moles of sodium hydroxide will be the double of the previous one, means sulfuric acid, because 1 mole sulfuric acid neutralizes 2 moles of sodium hydroxide. So finally we are getting 0.00604. Step 3, calculate the concentration of sodium hydroxide. Now we already got the number of moles of sodium hydroxide, moles, and we also know the volume. Now we can calculate the concentration in mole per dm cube equals to number of moles of solute in mole divided by volume of a solution in dm cube, and this is the number of moles from step 2, and this is the volume, and after doing it we are getting 0.242 mole per dm cube of sodium hydroxide. This is the concentration. Are you with me? Okay, it's very nice to calculate. Deducing stoichiometry by titration, and it's problem solving 10. 25.0 cubic centimeter of 0.0500 mole per dm cube solution of a metal hydroxide was titrated against a solution of 0.200 mole per dm cube hydrochloric acid. It required 12.50 cubic centimeter of hydrochloric acid to exactly neutralize the metal hydroxide. Deduce the stoichiometry of this reaction. So solution, step 1, calculate the number of moles of each reagent. We have to calculate the number of moles. Moles of metal hydroxide equals to concentration in mole per dm cube multiplied by the volume of solution in dm cube is equals to 0.0500 into 25.0 divided by 1000, and it's equal to 1.25 into 10 to the power minus 3 mole. All the informations are given. So we are getting the moles of hydroxide, metal hydroxide, we already get it. Now we have to find out the moles of another one by the next slide. Moles of hydrochloric acid equals to concentration in mole per dm cube multiplied by volume of solution in dm cube by the previous formula, 0.200 into 12.5 divided by 1000 equals to 2.5 into 10 to the minus 3 mole. Step 2, reduce the simplest mole ratio of metal hydroxide to hydrochloric acid, and this is 1.25 into 10 to the power minus 3 moles of hydrochloric acid ratio 2.5 50 into 10 to the power minus 3 moles of acid. So this is the stoichiometry or the mole ratio. Okay, now after doing it, we are getting 1 mole hydroxide is to 2 acid. So we have to write the equation finally. Metal hydroxide MOH whole 2 plus 2 HCl means 2 moles of HCl. So 1 mole metal hydroxide reacting with 2 moles of hydrochloric acid to form metal chloride plus 2 moles of water. That's all. Again, calculations involving gas volume using the molar gas volume, also Avogadro's hypothesis. So what is Avogadro's hypothesis? We have to know. Avogadro's hypothesis states that equal volume of all gases at the same temperature and pressure contains equal number of particles. All gases contains in same temperature and pressure in equal volume the equal number of particles. Don't forget it. All of them are in gaseous state. The molar gas volume is the volume occupied by 1 mole of any gas at a room temperature and pressure, which is in short RTP, room temperature and pressure. The molar volume is equal to 24 dm cube, 24,000 cubic centimeter. In short, in a smaller unit we can also write it. We can use the molar gas volume of 24.0 dm cube at RTP and to find the volume of a given mass or number of moles of gas, the mass or number of moles of a given volume of gas. Again, we want to see gas volumes and stoichiometry, and problem solving 11 will illustrate more practical example how we can relate stoichiometry and gas volume. Calculate the mass of methane CH4 present in 120 cubic centimeter of methane. Very simple question and easy to calculate. Here relative molecular mass value for methane is given 16.0. Solution, look at this, 120 cubic centimeter is 0.120 dm cube and we are getting it by dividing 1000 because we know the factor to convert cm cube to dm cube is nothing but 1000. 1000 cubic centimeter is equals to 1 dm cube. So after doing it, we are getting 0.120 dm cube. Moles of methane equals to volume of methane in dm cube divided by 24.0. This is the molar gas volume at RTP. And after doing it, 0.120 divided by 24.0 equals to 5 into 10 to the power minus 3 mole. Mass of methane will be now what? This is the number of moles and this is the relative molecular mass. Multiply each other to find out the mass of methane. Okay, so 0.080 gram methane is present here. Okay, I think all of you are getting me. Are you with me? Yes, all of you are understanding, no doubt. Gas volume and stoichiometry, problem solving 12, book question 11. When ammonia gas and hydrogen chloride gas mix together, they react to form a solid called ammonium chloride. So now we are solving the question from the exercise, book question 11. If you search your book, course book, I already give the information about the course book, and if you search the question number 11, you will get here, write a balanced equation for this reaction including state symbols. Calculate the molar masses of ammonia, hydrogen chloride and ammonium chloride. Look at this, marks are also distributed here. And question number C, what volumes of ammonia and hydrogen chloride gases must react at RTP in order to produce 10.7 gram of ammonium chloride? 1 mole of gas occupies 24 dm cube at RTP. Marks for this question is 3. Total marks here 8. Okay, so like exam style question. So we want to see the solution of this. Solution for A, you are asked to write the balanced equation. 1 mole ammonia gas reacting with 1 mole hydrogen chloride gas to form 1 mole of ammonium chloride as solid. And for B, relative molecular mass of ammonia gas is equals to 1 atom of nitrogen means 14 into 1 plus 3 atoms of hydrogen means 1 multiplied by 3 equals to 17 gram. Relative molecular mass of hydrogen chloride gas equals to 1 into 1 plus 35.5 multiplied by 1 because all the atoms are here 1 and 1, that is hydrogen 1 atom and chlorine 1 atom, that's why multiplied by 1, 1. Calculating this, we are getting 36.5 gram. MR of ammonium chloride equals to 14 multiplied by 1 plus 1 multiplied 3 plus 35.5 multiplied by 1, and this is equals to 53.5 gram. Part C, what is the calculation? 53 gram of ammonium chloride is formed from 24 dm cube of ammonia. Look at this, we are relating here mass with volume, so this is important part. Therefore, by unitary method we can say 10.70 gram of ammonium chloride will be formed from where? 24.0 multiplied by 10.70 divided by 53.5, and after doing calculation we will get 4.80 dm cube of ammonia product. Therefore, we can say 4.80 dm cube of ammonia and 4.80 dm cube of hydrogen chloride gas must be required at RTP in order to produce 10.7 gram of ammonium chloride. And that's all. Thank you for joining and watching. Any question? Please ask on the comment box if you have any query. Thanking you again for watching next video. Bye bye. See you again.